Okay, so here it goes. Ready, guys? Okay, now look, all the functions that we've differentiated up to this point are called, excuse me, sorry, they were all in explicit form. And what I mean by that, sorry guys, I can't clear my throat. What I mean by that is they're in f of x equals form or y equals form. Okay, and so when they're in that form, we just use all the rules you know up to this point, right, to find the derivative. Okay, so this is what's going to change today. We're going to need to differentiate functions that are not in that form. Like, for example, look at that equation, look at that equation. You see how those are not in y equals form? You see those are not solved for y? Guys, don't miss this. You see how those equations are not solved for y? Okay, and by the way, when an equation is not solved for y, we call that implicit form, in case you didn't know that. And so how do you think we're going to differentiate such equations? Well, we're going to use a process called implicit differentiation. Okay, now, before I get into how to use that process, I've got to show you some things that are kind of a little part of that process. Okay, so here's what I want you to understand. When I've been finding the derivative f prime of x or dy dx up to this point, again, clearly we're differentiating with respect to x, right? So for example, if we differentiated x cubed with respect to x, you just got 3x squared and you were done, right? No big deal. Now, here's what's going to happen. I'm going to change things up on you. And I'm going to ask you to differentiate something like y cubed. Not with respect to y, but with respect to x. And so once I do that, basically y is some function of x. Okay, we don't know what it is, but it is some function of x. So with all that in mind, you should look at that as being a composition then, where y is the inside function and y cubed is the what? Outside function. So in that case, wouldn't I need to use a chain rule then if I'm taking the derivative of a composition? And how does the chain rule work? Well, for example, if I were going to take the derivative of y cubed with respect to x, again, here's how the chain rule would work. I would take the derivative of the outside, which is this. Everybody agree with that? Now watch this. I would also need to then finish the chain rule by multiplying by the derivative of the inside. And if you think about it, if the inside function is y, then, and you're differentiating with respect to x, then wouldn't the derivative of the inside be dy over dx, right? The derivative of y with respect to x, right? Okay? All right, well watch. I got to keep showing you these until you see the pattern. Because if you don't see the pattern, you're going to have no idea what I'm doing or why it works. Okay, so watch. Hopefully you start to see a pattern. Ready? You watching? Yes? Okay, so here it goes. What if I want to take the derivative of y cubed with respect to t? How would that work? Well, again, I would use the chain rule. There's a derivative of the outside. Everybody agree? And then times the derivative of the inside. What would the derivative of the inside be? dy over dt, right? Derivative of y with respect to t, right? Okay, what if I take the derivative of y cubed with respect to p? How would that work? Again, chain rule. Take the derivative of the outside, which is just 3y squared, and then times the derivative of the inside, which would be the derivative of y with respect to p. In other words, dy over dp, right? Are you following me? Are you starting to see a pattern? Okay, because watch, something's going to happen here. Okay, what if I took the derivative of h cubed with respect to x? What would that look like? Well, again, by the chain rule, that's the derivative of the outside, and then times the derivative of the inside, which would be the derivative of h with respect to x, right? dh over dx, right? All right. Watch this. How do I take the derivative of h cubed now with respect to h? What would that be, guys? That would just be what? What would it be? 3h squared. I wouldn't need anything after it, would I? Because I'm differentiating with respect to the variable h. You see the difference there in all of those? Now wait a minute. Why don't I multiply by anything else? Why not? Well, let's suppose I did. what would it be? It would be 3h squared times what? dh over dh. But what is dh over dh? 1. And so that's why we don't even need it. So it's just 3h squared. Do you understand? Yes? Good? Okay. And so at that point, I think you should see why I'm doing what I'm doing today. Okay? Now, again, that was just one very, very small piece of what we're doing today. Now you're going to see where I use that in a bigger process. So what I'm saying is, based on everything I just said, when you differentiate with respect to the same variable you're working with, you just differentiate as usual, right? However, when you differentiate with respect to a different variable than you're working with, you got to use the chain rule and multiply by d something over d something. Got it? That's what I want you to remember from all that. Okay, now, so with that in mind, now I'm going to actually show you the major process for today. So this is how you take the derivative of an equation that's not solved for y. Okay, so again, this is the process you use to find the derivative equation, dy dx, for an equation that is not in what? Not in y equals form. Okay, so the first step is this. Ready? You're going to differentiate both sides of the equation with respect to x, unless they tell you otherwise, right? One term at a time. And go back to middle school. How can you tell a term? A term is separated by what? Additions or subtractions, right? Got it? Okay. So make sure you differentiate one term at a time. Now, while you're doing that, there are two things you got to remember. A, what? When you differentiate a term with x, you just what? Just differentiate as usual, right? Like I explained a minute ago. However, what if you differentiate a term with y? Then you must multiply by what? dy over dx, as I explained a minute ago, due to the chain rule, right? Okay? Now, once you're done with that, the calculus is done, okay? And so the rest of it is algebra. But again, as usual, that's typically the hard part. So what are you going to do then? Well, you're going to move all the terms with dy dx to one side of the equation, move all other terms to the other side. Are you with me? And then factor out a dy dx if you need to, and then finish solving for dy dx. Okay, it sounds complicated, but after a couple examples, I think you'll get the hang of it, although I'm going to do several more examples because the ones I picked are all kind of different in their own way. Okay, so now the good news is the first couple examples I typed up for you so you don't miss anything while you're paying attention rather than sleeping, right? With me? Okay, so watch. I typed them up so you don't have to miss anything while you're trying to write it down. So just follow along. Are you ready? Notice, what about this equation? Is it in y equals form? Definitely not. So the only way I'll be able to differentiate it is to use what? Implicit differentiation. And again, it's a process. It's not a formula. Okay, so what do? What is the first thing I do? I differentiate what? One term at a time. And anytime I differentiate a y, I got to put a what? I got to multiply by dy dx. Okay? All right, so here we go. What's the derivative of that term? Quick. 3y squared, but then I got to multiply by what? dy dx, because I just differentiated a y, didn't I? Okay, plus. What's the derivative of y squared, guys? 2y, and then I got to multiply by dy over dx, because I just differentiated a y. Minus, what's the derivative of 5y, guys? 5, and I got to put a what? dy over dx. I got to multiply by dy over dx due to the chain rule. And then minus, what's the derivative of 2x with respect to x? I'm sorry, what's the derivative of x squared, I should say? 2x. You see I don't need anything after that? Yes? And then again, remember, this is no different than Algebra 1. If you want to keep the two sides of the equation balanced, whatever you do to one side of the equation, you got to do the same to the other side. So don't forget to take the derivative of that side as well. What's the derivative of negative 4? 0. Okay, be careful. That's where you're going to make a mistake. You're going to get so caught up in taking the derivative of the left side, you're just going to accidentally bring down to negative 4 and you're going to forget to take the derivative. Please don't do that. Make sure you take the derivative of both sides. Is that clear? Okay, so again, the calculus is done. Now it's all what? Algebra. So you got to know what to do now. What do I do now then? I what? Yeah, move terms around. Get all the dy dx terms on one side, all the other terms on the other side. So really, the only thing I have to move is this, right? I'm going to move that to the right side by adding it. Yes? Okay, what happens now? Well, what do you notice on all three of those terms now? You can pull out a what? dy over dx. So after you pull out a dy over dx, doesn't that take you to here? Doesn't it? And then finally, if you divide both sides by that, you're pretty much done, aren't you? And there you go. So what is this? What did I just find? What is that? That is my derivative equation, isn't it? And again, what have we been using derivative equations for the last month? To do what? To find slopes at points on the original curve. Now look, something changed today. Normally, when you find the derivative equation or derivative function, you're just plugging in the x value, right, to get the slope? But now look, now your derivative formula has what? Both x and y. So when the time comes to find the slope at a point, you're going to have to plug in both the x and the y value of the point. Do you understand that? Yeah? Might want to eat some of that candy to stay awake. All right? You with me? Okay or not? Yeah. Okay, so again, I typed up this one so you don't miss anything. Everybody watch. Heads up. Everybody with me? Okay. Now what happens? Again, terms are separated by additions and subtractions. So the first thing I got to do is take the derivative of that whole term, don't I, right there? Don't I? And when I look at that, it's a what? It's a product where both pieces have a variable. So you absolutely must use the what? Product rule. Okay, now watch. So how does it, by the way, again, you should look at that as being the product, x squared times y. Everybody with me? So I'm going to use the product rule. Here it goes. Derivative of the first function, which is 2x, times the second function, which is y, plus the first function, which is just x squared. And now be careful. Now I got to multiply by the derivative of the second function. What's the derivative of y? 1. But then I got to multiply by what? dy over ds, because I just differentiated a y. Is that clear? Okay, keep going. Minus, okay, what's the derivative of 5x? 5. And then finally equals, what's the derivative of 3? 0. Any questions on what I did there? No? Okay, now I just got to clean it up. So what I did is I cleaned it up here. And then get all the dy dx terms on one side, move everything else to the other side. So that means I got to move this. Don't I got to move that to the other side? Right? And so I just subtracted it. That got me to here. And then finally, I think you can all see that the last thing I need to do is get rid of that by dividing both sides by that. Yes? And so if I divide both sides by x squared, I'm done with that one. There's the derivative equation for the original equation. Is that clear? Okay, now the rest of them you're going to have to write down. So I want to see everybody writing these down. Write small. Okay, you're going to have to write small to fit this in here. And that goes for the next page as well. All right, so here it goes. I'm going to use separate paper so I don't have to write so small. Ready, guys? Okay. And you're going to help me with this. I'm going to call on you guys, and you guys are going to help me. Okay, so there's the equation that we want to find the derivative of, and clearly it's not in y equals form, is it? No, so we're just going to have to use implicit differentiation, right? Okay, so here we go. All right, how about Frank? Ready? I'm going to start by taking the derivative of that term. What is it? 3x squared, okay, plus, now I'm going to take the derivative of that. What is it, Frank? Okay, 3y squared, good. And then you got to multiply by dy over dx. Everybody with me? Okay, equals. I'll let somebody else do the other side. Trevor. Now I got to take the derivative of this. What is it? 3. And then plus, what's the derivative of that? 0. Okay, any questions on that? So now, at this point, again, you want to get the dy dx terms on one side, move everything else to the other side, right? And so clearly I'm going to move that to the right side by subtracting it. And then finally, I think you'll all agree that we're going to finish solving for dy dx by dividing both sides by that thing right there. Everybody with me? Yes? Okay. Jason with me? Okay. And so if I divide by 3y squared, if there's something you can simplify, please do that. So I think you'll agree you can pull out a 3 on top, right? And then at that point, whoops. me do that again. So it's 1 minus x squared, right? And then once you do that, you can cancel out the what? The 3's. Okay. Okay, so there's my derivative equation, right, for the given equation. Any questions on this? Okay. All right, now, in part B, what are we going to do with that? We want to find the what? The equation of the tangent line, correct? All right, so here it goes. Everybody get this down, because then you know these are going to show up on the next test. You know they will. And if you don't have them written down, you're not going to have anything to study, are you? Okay, so again, please write these down. Okay, so here's the original equation, right? And we want to write an equation for the tangent line at the point where x is 2, right? Well, again, here's the derivative form that we just found, isn't it? 1 minus x squared over y squared, is that right? And so we're at the point 2 something, aren't we? Don't I need the y value here? Because eventually I'm going to plug the x and y into there to get the slope at that point, aren't I? So how do I find the y value here? What do I do? Substitute the 2 into where? Yeah, into this original function. Okay, so I'm going to have 2 cubed plus y cubed equals 3 times 2 plus 10. Everybody see what I'm doing here? I'm just plugging the x value into the original equation to get the y value at that point on the original equation. Right? Got it? And if you subtract 8 from both sides, you get that. If you take the cube root of both sides, you get that. Everybody good with that? Okay, and so now you're talking about the point 2 comma 2. When x is 2, y is 2. Good? Okay. All right, so if I take that point now and plug it into there, what will that give me? What will that give me if I plug that point into the derivative equation? It'll give me the slope of the curve or slope of the tangent line at that point. Okay, so plug it in. And what does that give me, guys? Negative 3/4, is that right? Okay. And by the way, when I checked homework a couple days ago, a lot of you on these types of questions didn't finish. I'm asking you for the equation of the tangent line, and some of you just stopped there. Is that the equation of the tangent line? No, that's just the slope of the tangent line. So how do I finish and get the equation of the tangent line? Put in point slope form. So it would be y minus what? 2 equals negative 3/4 times x minus 2. And some of you are skipping that and you're just writing the answer on Moodle. You guys, don't do that. I'm going to start taking points off. I don't want you guys just copying off Moodle. There's no reason not to show this first. And then if you want, you can change it to slope-intercept form. But some of you went right from the slope to the final equation with no in-between steps. Okay, yeah, you guys got to show your work. Got it? Okay or not? Okay. All right, so that is the equation of the tangent line, and you can just leave it in point slope form. Obviously, if you needed to graph that, you could easily change to slope-intercept form, right? Good? Okay. All right, now again, C is a typical AP question, and you know, if it shows up on my notes, you know it's going to show up on my test. So here we go, example 3C. Again, this is the only example like it I'm doing. Okay, we want to find all points on the original curve. Here it is. Here's the original curve. Where you have a what? Horizontal tangent line. Okay, what do you know about horizontal tangent lines? The derivative is 0. So you got to find where the derivative equals 0. Everybody with me? Yes? Okay, so take the derivative equation, which again was what? 1 minus, what was it? 1 minus x squared over y squared, is that right? and set it equal to 0. Any questions so far? Okay. So now the question is, when does that fraction equal 0? Well, when does any fraction equal 0? Yeah, when the numerator is 0. So now it just boils down to figuring out when that's 0. Everybody agree? And by the way, if you solve for x, I think you'll all agree that it's what? Positive or negative 1? Okay, so what that means is there may be actually what? 2 points on the original curve. We have a horizontal tangent line, right? Okay, and so how do I find the y values for these points? Plug them into where? The original equation. These are points on the original curve, so plug them into the original equation. Ready? So I'm going to put a negative 1 there. I'm going to put a negative 1 here. This is what, 7. Add 1. And I think you'll agree that y is 2, yes? Is that right? Yes? And then do the same thing here. See, if we subtract 1, we get 12. You take the cube root of both sides, and you get the cube root of 12, right? So there you go. So there are actually 2 points. By the way, what would happen if you plugged one of these x values into here and it gave you undefined? Then what? Then there what? There wouldn't be a point there, right? Does that make sense? Right? Okay. Good? So if you graph this somehow and looked at it, there'd be 2 points where the original graph would be flat, so to speak, right? Got it? Okay. All right, now the next page, again, you're going to have to write really small to fit it in there. Okay, and again, if you look at them, they're not repetitive at all. If you look at the next 4 examples, they're all different, aren't they? Yes? Aren't they all different? So make sure you get them all down. Just because you understand one doesn't mean anything, okay? Because the other ones are definitely different. Okay, so here we go. Here's example 4. Okay, so we got x squared minus 3xy plus y cubed equals 10. Ready? And it said, again, find the derivative. If I'm not telling you otherwise, always assume you're differentiating with respect to x. Is that clear, unless I tell you otherwise? Okay, and so in this case, we're going to do, again, everybody agree you're going to have to use implicit differentiation here? Everybody agree? Because it's not solved for y? So here we go. Quickly, everybody, what's the derivative of that? 2x. Okay, now here's where we run into trouble, right here. That's definitely a product, right? Now it's up to you what you want to do with that 3. You can pull out the 3 with the subtraction and distribute it later. Or if you want, you can just leave the 3 with the x and deal with it that way. And I think that's the way I'm going to do it. So here's the deal. I am going to use the product rule on that. And whatever I get, I'm going to put in brackets. And why would I want to put it in brackets when I take the derivative? So I remember to do what? Distribute the minus later on. Understand why I'm putting it in brackets? Yes? Okay, so here it goes. Clearly, that's a product of variables, right? A product with variables on each piece. And so I'm going to have to use the product rule. Here it goes. So I take the derivative of the first function. What is it, guys? What is it? Hello, can't hear you. 3, okay. Derivative of the first function, which is just 3, times the second function, which is just y. And then plus the first function, which is just what? 3x. And now, be careful, times the derivative of the second function. What's the derivative of y? 1, but then I got to put a what? dy over dx. Again, due to the chain rule, as I explained at the beginning of the hour. Yes? Okay, and then continue. Plus, what's the derivative of that? 3y squared times dy over dx. That's right. And then equals, don't forget, what's the derivative of 10? 0. Okay. All right, so at that point, I'm going to clean it up, and don't forget to distribute your subtraction here. Don't you have to distribute the subtraction here? Yes? Okay, so this is what I get now. Any questions yet? Any questions yet? No? All right, now what do? What's next? I do what now? Yeah, get the dy dx terms on one side, move everything else to the other side, right? Let's do it. So clearly I'm going to move these to the right side, aren't I? Okay, let's do that. Be careful. By the way, you guys, let me say something before I forget. When you're doing these on a test, please double and triple check that step right there, because if you make one little mistake there, like if you forget a dy dx, the rest of it's going to be a huge waste of time, isn't it? You don't have that kind of time to waste when I put, 6 or 7 of these on a test, right? Got it? So be careful. When you're doing this on a test, please double and triple check that first step, and then continue. Okay? All right. And now once I get the dy dx terms on one side, clearly I'm going to pull out the dy dx, right? Okay, and so that leaves me with this, right? And then finally, I'm going to divide both sides by that, right? And I'm pretty much done with this one at that point, unless there's some simplifying to do. Now, I know I can pull out a 3 in the denominator, but I can't cancel it, could I? No. And so I guess I can just stop there. Yes? Good. Any questions before I move on? We're good? Yes? Okay. All right, example 5. Again, I think you're going to agree with me when I say this is definitely different than the last one. Yes? Okay. All right, now I want to talk about this. Again, what I'm about to show you, you don't have to do. It's just an option. Ready, Frank? Okay. So, could I divide by 2 right now before I do anything? Yeah, why not? Okay, again, you don't have to do that, but well, that'll do is just it'll make the rest of it a little bit easier, won't it? You won't have to worry about that 2 anymore on the left side when you're taking the derivative. Okay, again, you don't have to do that, but it does make it easier. Agreed? Okay. All right, so now I'm going to go ahead and definitely I have to use what? Well, yeah, the product rule, but in general, I'm going to have to use implicit differentiation, right? Because the equation is not in y equals form, right? Okay. And so again, this is all one term, isn't it? Isn't it all one term? And so I have to use the product rule because it's a product where both pieces have a variable. Yes? Okay, so be careful. Watch this. So I'm going to use the product rule by taking the derivative of the first, which is just cosine, right? So that's the derivative of the first function, times the second function, and now plus the first function, and then times the derivative of the second function. This is where you're going to make your mistake right here. When I go to take the derivative of that, what's the derivative of cosine? Negative sine, right? Y, right? Now, wait. Even though I didn't do that back here, I could have. What I'm supposed to do is technically now go and take the derivative of the inside. So what's the derivative of y, guys? What's the derivative of y? 1, and then I got to put what? A dy dx. Everybody catch that? Okay. Now, I know I didn't do that here. I know I didn't go inside and take the derivative of that, but if I did, what would it have been? It would have just been what? 1. So I really didn't need to do that there. Does that make sense? Yes? So it's only really important that you follow through on that detail when you're differentiating something that has y in it for obvious reasons. Okay? All right, now equals, what's the derivative of a half, guys? 0. Got it? Please don't forget to take the derivative of that half. That's where you're going to mess up right there. You're going to forget to take the derivative of the other side. Don't do that, okay? Una, with me? Okay. All right, let me clean this up. Something strange is going to happen, by the way. And by the way, that turns that into a subtraction, doesn't it? Oh, here. Why do you think I moved that dy dx to the front there? Why do you think I moved it from there to here? Why? Exactly. So you don't think that the dy dx is inside the sine function. It's not, is it? It's times the whole thing. So I pulled it out front just to make sure you see that. The dy dx is not inside the trig function, is it? No. Okay, so be careful. Okay, so now at this point, I'm going to get the dy dx term on one side, everything else on the other. So clearly I'm just going to move that to the other side by subtracting it. Okay, everybody should be writing this down. That's part of your participation grade, right? And then at this point, you what? How do you solve for dy dx now? What do you do? Yes, something wrong? Yeah, it should be negative. Yes, thank you. All right, there you go. I subtracted that from both sides, didn't I? Thank you. All right, so now if I divide both sides by that, that, and that, I'll be good. Yes? Okay. All right. Now, watch what happens. Obviously, those cancel, yes? All right, and what you're left with, if you think about it, you're left with this fraction, right? But can't you, if you want, can't you think of it as that fraction times that fraction? Isn't that the same thing when you multiply fractions? Yes? And why would I want to do that? Well, what is cosine of x over sine of x? That's the same thing as what? Cotangent of x, exactly. Same thing here, right? This is the same as what? Cotangent of y. And so, you guys, I can't emphasize how important it is for you to check your answers on Moodle. Because I'd like you to simplify your answers exactly how they do on Moodle, because that's the way I'm going to do it when I'm making up the answer choices for the test, right? I'm going to simplify the way I've been teaching you to simplify. And if you can't simplify, you're never going to be able to pick out the answer from the 5 choices, are you? No. Okay, so you have to make sure you simplify your answers. Okay. All right. Example 6. Again, you're going to see this is very, very, very different. Any question on example 5 before I move on? No? Everybody good? Okay, here we go. Example 6. All right, so when you look at this, again, clearly it's not solved for y, is it? Is this thing solved for y? No. So you're going to have to use what? What's it called? Implicit differentiation. So here we go. All right, when I go to take the derivative of that, what is it? It's a what? It's a composition, right? The outside function is cosine, the inside function is x plus y. So clearly you're going to need the what? The chain rule, right? Okay, watch. This is tricky. Watch. Watching back there? Yes? Okay, here it goes. Start by taking the derivative of the outside. So everybody, what's the derivative of cosine? Negative sine. And then aren't you supposed to put the inside back in the way it is? And then you finish the chain rule by multiplying all that by the derivative of the inside. Are you ready to take the derivative of the inside? Here we go. What's the derivative of x? 1. Plus what's the derivative of y? 1 times dy over dx. Anytime you differentiate a y, you got to multiply by dy over dx. Got it? Okay, and then equals, what's the derivative of that? 1. Any questions on that? All right, now we're definitely not done because we have some options, and we need to talk about those options because sometimes one option will be better than another option. Okay, everybody with me so far? You see what I have up here? Yes? By the way, you're not going to look at that and say, oh, 1 plus 1 is 2, so that's 2 times dy dx, right? Wrong. No, 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 no. Don't be doing that, please. The dy dx is only multiplied by this 1. Is that clear? Okay, don't make that silly mistake. I hope you don't do that. Okay? All right. All right, let's talk about our options. What are our options to finish this? Please watch. You need to know both options. Trust me. What are my options to finish solving for dy dx? Well, I could divide both sides by that, right? And at that point, I just subtract that 1, and I'll pretty much be done. Everybody agree that that's one way to finish it? What's the other option, though? Distribute. I could distribute this to there and to here, and then finish it from there. All right, now let me say something about those options. On this particular problem, I don't think it matters which of those two options you use. However, what if there was a dy dx term over here? Well, if there was a dy dx here, and you divided by this, you'd be stuck. You'd be stuck with a mess. And so what I'm saying is you need to know both options. And if one option gets you stuck, then go back and do the other option instead. Is that clear? Yes? Okay, so in this one, I don't think it really matters. So I'm just going to go ahead and divide both sides by that. And that's going to leave me with this. Everybody with me on this? And now I'm going to subtract 1 from both sides. Is that okay, guys? And so basically you end up with that. Yes? All right, now, what are your options now? Well, you could get a common denominator, right? Everybody agree you could get a common denominator now to bring them together under one fraction? Okay, again, I want to keep getting you guys used to those common denominators because when we do applications, you're not going to want to stop there ever. You're going to definitely want to keep going and get a common denominator. So that's one option. However, watch this. You tell me, what's 1 over sine the same as? 1 over sine is the same as what? Cosecant. So if you want, you can just change that to negative cosecant of x plus y. And once you do that, you no longer have a fraction, so you don't have to worry about a common denominator. Make sense? Yes? But again, you could have gotten a common denominator. That would have worked out okay too. Okay? Okay, with me, Matt? Okay. All right. All right, one more of these, and then we'll move on to something completely unrelated. So this is the last implicit differentiation example you're going to get. And again, it's different. What's different about it? Yeah, I'm asking you to evaluate the, or find the slope of the tangent line at a point. So watch, I'm going to show you a little trick. So everybody get this down, please. I think you'll like this trick. Okay, well, let's just talk about what we're going to do before we do it. What are we going to do right now? We're going to use implicit differentiation to do what? Find the derivative, and then at some point we're going to plug in the what? 0.11 to get the slope at that point? Okay, so here it goes. Real quick. All right, you guys are going to help me. How about Chaz? What do I do here to find the derivative of that? What is it? It's just what? 2x. Okay. Frank, what's the derivative of that? What's that? Differentiate the y squared. What do you get? 2y times dy dx. Good. And then over here, we have a what? We have a what? Product. So we're going to have to use the product rule, right? As long as both pieces have a variable, we have to use the product rule. Okay, so here it goes. So I take the derivative of the first function, which I think you'll agree is 8x, times the second function, which is just y, right? Plus the first function, which is just 4x squared, and now times the derivative of the second function. What's the derivative of y, guys? 1, but then you got to multiply by dy over dx. Any questions on that? Any questions? All right, now watch what's going to happen. I'm going to clean it up first. Okay, so hold on. Oh, sorry. All right, so now what I would normally do is I would get the dy dx terms on one side, everything else on the other side, and keep going, right? However, after I do that, what am I going to end up doing? I'm going to end up doing what? Plugging in 1, 1. Well, if I'm going to do it a couple steps from now, is it okay if I do it right now instead? Sure. I've already taken the derivative, right? So at this point, if I want, I can go ahead and stick in the 1, 1 right now. Again, you don't have to, but what that'll do is it'll actually make this less messy, won't it? Yes? So it'll actually help if I did it. You don't have to do it, but it definitely makes things easier from this point forward. Okay, everybody see what I'm doing now? I'm just going to plug in the 1, 1 and then solve for dy dx. Yes? Good? Okay. Again, be careful, guys. That is not 4 dy dx, is it? Is it? That's not 4 dy dx, is it? No. Okay, so at this point, again, I'm going to get the dy dx terms on one side, everything else on the other side. So what I'm going to do is this. I'm going to move this to this side, and I'm going to move that to this side. Does that make sense, guys? Does that make sense or no? Okay, so let's do that. Okay, and then, obviously this is 6. Now, there's a couple ways you can deal with this. You can go ahead and pull out the dy dx, and that'll leave you with 2 minus 4, which is negative 2, right? Or you can just look at it as being like terms. And if you look at it that way, what's 2 dy dx's minus 4 dy dx's? That turns into what? Negative 2 dy dx's, if you look at it like that? Yes? Okay. And then finally, just divide by negative 2, right? We're done? Agreed? Okay. And so what do you get? The slope of the tangent line at the point 1, 1 is what? Negative 3. Everybody okay with this? Yes? All right, now the last page is actually going to go pretty quickly, I think. And most of it's already typed up, so I ask you to stay awake, right? All right, this is clearly completely unrelated to what I've been doing today, yes? Totally different concept. Okay, so think about it. We've taken derivatives of a lot of different functions so far, haven't we? The one thing we haven't done yet is take derivatives of inverse trig functions or arc trig functions. And so basically I'm giving you these 6 formulas. Now, if you want to know where they come from, you can always look in the textbook. The textbook, derives just about everything. So you can see how you can come up with these formulas if you're interested. I'm not going to make you know that. As long as you can use these formulas to give me some derivatives, I'm okay. Okay, now let me talk about this. There's good news and there's bad news about these 6 formulas. The good news is, for my next test, I'm not going to make you memorize them. I'm just going to give them to you. But remind me if I forget, okay? Remind me. Okay, the bad news is they're not going to give them to you on the AP test. Okay, back to some good news. The good news is they don't show up every year, and when they do, it's maybe just 1 at the most. Okay, so there's good news and bad news. So the bottom line is, just before the AP test, you might want to memorize them just to be safe. Okay, back to some good news. The good news is, once you memorize this, right, once you memorize the formula for the derivative of the arc sine function, isn't this exactly the same except what? Except it has a negative, right? And once you memorize that, this is the same thing except it has a what? Negative. And once you memorize that, this is the same thing except it has a negative. And so really then, you only have 3 things basically to memorize, yes? Okay, all right. But again, right now I'm not going to make you memorize it. I just want to make sure you can use it. Ready? So I did a bunch of different examples. Again, they start out very easy and then they get really nasty. So stay with me. Okay, I didn't make you write any of this down. It's all typed up for you. Just stay awake. Got it? Yes? With me? Frank, with me? Yeah? Okay. Yeah? Okay. All right, just you weren't looking up here. Okay. So right away, guys, I ask you to take the derivative of the arc sine of something. Now, isn't that my u, so to speak? Isn't it? So right there, look at this formula number 1. How do I find the derivative of the arc sine? Well, the formula says you take what? The derivative of u, which is what? What's the derivative of 2x? 2, and then over the square root of 1 minus your u squared. So 1 minus the whole 2x squared. Notice how I put the 2x in parentheses. Why did I do that? So I remember to square the whole thing. Okay, so what's 2x squared? 4x squared. Okay, so that's my answer. Any questions on that one? They're going to get harder, trust me. Okay, another one. How do I take the derivative of arctangent of 3x? Well, again, you got to look at that as being your u. Isn't my u 3x? And so what's the formula for that? The derivative of u over what? 1 plus your u squared. So real quick, what's the derivative of my u? What's the derivative of 3x? 3. And then over 1 plus the whole 3x squared. Yes? And when you square the whole 3x, you get 9x squared. And we're done with that one. Any questions? Pretty easy, right? Just follow the formula. All right, now this one's tricky. Isn't this my u right here? Isn't it? And for derivative purposes, is it okay if I write that as x to the 1/2? Is that okay with you guys? Okay, so again, the derivative of the arc sine is what? The derivative of u. Everybody agree that the whole thing is the derivative of u right there? Over what? The square root of 1 minus your u squared. And by the way, when you square a square root, don't those cancel out? That's how I got this. And then what happened? Well, since that had a negative exponent, I moved it to the denominator to make it a positive exponent, and then I turned it into the square root. And that half on top I can fix by just putting that 2 in the denominator. Is that clear? Yes? And then what did I do? What did I do from there to my answer? What in the world did I do? Yeah. Since those are both square roots, can I combine them under one square root? When you multiply square roots, can't you combine them under one square root? And then I distributed the x, so I distribute the x to there and there. That's my final answer. And again, you're going to have to simplify to that. Because if I asked you to find the slope at a point, I don't think you want to plug a value back into here, do you? No. Wouldn't this be pretty easy to plug an x value into if I asked you for the slope? But you don't want to do it back here. So you see how important it is for you to simplify as much as you can? Yes? Okay. All right, now watch this one. This one's really bad. This is my u, isn't it right there? Okay, and so again, if you look at the formula to take the derivative of the arcsecant of u, you take the derivative of u over the absolute value of your u times the square root of your u squared minus 1. Are you following all that? Make sense? Okay, so what is that supposed to be? That's the derivative of what? E to the 2x. What's the derivative of e to the 2x? E to the 2x times the derivative of 2x, right? Which is 2. Everybody agree that's where I got that? Yeah. Now watch. All over the absolute value of my u, and then times the square root of my u squared minus 1. Now, obviously, when you have a power to a power, you multiply them, giving you a 4x there. Now wait, what happened to my absolute value? Where did it go? Well, if you draw a rough sketch of y equals e to the 2x, isn't it always above the x-axis? And so isn't it always positive? So do I really need the absolute value on the e to the 2x? No, I dropped out the absolute value. And then at that point, what can I do? I can do what with those? Cancel them. And there's my final simplified derivative. Is that clear? Okay, 2 more and we're done. Can you handle that? All right, now this one's pretty nasty, so watch. Watch what I'm doing here. All right, so again, to take the derivative, I have to start by taking the derivative of that, and that's just the simple formula, right? That's my u, and so I take the derivative of u, which is 1, over the square root of 1 minus my u squared. So everybody agree that's just the derivative of the first piece? All right, now, plus, what's this? This is a what? That's a what? It's a product. So I should think of it as x times what? Well, for derivative purposes, is it okay if I rewrite it like that, guys? Are you okay with me on that? And so here we go now. We're going to have to take the derivative of that product using the product rule. Watch. So I take the derivative of the first function, which is that, times the second function, which is that, plus the first function, which is that, and then times all of this, which is the derivative of the second function. Everybody see that whole mess there is the derivative of this right here? Do you see that? Okay, then what did I do? How did I clean it up? Well, the 2's canceled. Since this had a negative power, I took it to the bottom and turned it into that square root right there. this x times that x turned into an x squared. Are you following me on this? That negative right there turned that addition into a subtraction. Any questions so far? Still not done. Okay, then what did I do? Then I got a what? Common denominator. Well, so basically all I needed to do is multiply that by the square root of 1 minus x squared over the square root of 1 minus x squared. And I didn't show all the steps, but when I do that, don't I get that instead in the middle there? Don't I? And then once you have a common denominator, don't you just keep that denominator and take that plus that minus that? And all that simplifies to that, doesn't it? And by the way, if you want, you can pull out the 2. So now look, you can stop there, however, because remember I said if you have a if you have a variable inside the square root in the denominator, I said that's the one time you don't have to get rid of the radical in the denominator. Remember I said that? Okay, so you could stop if you want there. But if you did decide to get rid of the radical in the denominator by multiplying top and bottom by that square root, after you simplify, it actually simplifies really nicely down to that. Again, you didn't have to do that, but just so you know what I did, that's what I did. Are you with me? All right, one more very easy one and we're done. Okay, you're going to help me with this one. Okay, last one. All right, so what are we going to do, guys, when I go to take the derivative? What are you looking at big picture here? You're looking at a product where both pieces have a variable, don't you? And so you're going to have no choice but to use the what? Product rule. Here it goes. Ready? You take the derivative of the first function. Everybody, what is it? 1. Good. Times the second function. So I'm just going to copy the second function, right? Now, plus the first function, which is what? X. And now times the derivative of the second function. Aren't I going to need the formula for that? So here it is. How do I find the derivative of arctangent of u? What is it? It's the derivative of u over 1 plus u squared. Everybody agree? Okay, and so this is my u. And so what is it? 2x. That's the derivative of u over what? 1 plus x squared squared. Everybody agree with that? Okay, and now just simplify it and we are done. If you want, you can multiply those and give you a 2x squared on top, right? And then this is what? X to the 4th? Yeah, don't worry about a common denominator on that one. Good? Any questions?